Today we're going to go more in depth in rational functions and their graphs. So we're going to identify the properties of rational functions, specifically wholes, asymptotes, x-intercepts, and y-intercepts. So last time when we had the rational function, we just had a single number on top. Now we're going to have a full-on function on top. So p and q are both going to be functions. We're going to have zeros at each real value of x, for which p of x is equal to 0. That means we're going to set the top equal to 0 to get our x-intercepts. And we're going to have vertical asymptotes at each real value of x, where q of x is equal to 0. So we're going to set the bottom equal to 0 in order to figure out our vertical asymptotes. Now here's an example along with the steps to solve it. So our first step is we need to factor the top and bottom if possible. For our current problem, I can see that the top can be factored. Now that I factored the top to get x plus 4 times x minus 1, I'm going to set both the top and the bottom equal to 0 and solve for x. When I did that, for the top, I was able to get x is equal to negative 4 and 1, and those are going to be my zeros or my x-intercept. On the bottom, I was able to get x is equal to negative 3, and that's going to be my vertical asymptote. Our next step will be to substitute 0 into the x in order to figure out what the y-intercept is. And that's going to give me a y-intercept of negative 3/4. So our two zeros are going to be negative 4, 0 and 1, 0. Our y-intercept is going to be at 0, negative 4/3, and our vertical asymptote is at x is equal to negative 3. Remember, our vertical asymptote is a vertical line. Alright, let's run through a few more examples. Find the vertical asymptote, any wholes, and the x-intercept. So we have y is equal to 5 minus x over x squared minus 1, factor if possible. I know that I can factor the bottom. Then I set both the top and the bottom equal to 0, and I solve. This tells me that I have an x-intercept at 5, 0. And I'm going to have two vertical asymptotes, one at x is equal to negative 1 and one at x is equal to positive 1. And here I have no wholes. Now for the next problem, it's already factored for me, but if you notice, I have an x on top and I have an x on bottom. The x on top and the x on bottom can cancel each other out. Now let's go back up to our steps. Our steps said that if the factors on top and bottom cancel out, then the factor on the bottom creates a whole. And we'll look at a picture of this in a little bit. But for our purposes at the moment, what we see is that the x divided by x is going to cancel each other out. Now we're still going to solve just like we were doing before. So all that's left on top is an invisible 1. And then on the bottom, I'm still going to set it equal to 0. That gives me x minus 1 is equal to 0. X is equal to 1. Now, if I was to set the other factor equal to 0, and this is the key, you have to set both of these factors on the bottom equal to 0. So x is equal to 0. That means I'm going to have a whole right here at that 0, and I'm going to have the vertical asymptote at x equals 1. So I would say whole at x is equal to 0, and a vertical asymptote at x is equal to 1. Now for this, there aren't going to be any x-intercepts because if you notice, the variable on top canceled out and I have a whole there. So if we had actually solved the top, we would have had x is equal to 0, but I know that I have a whole at x equals 0, so I'm never actually going to touch that x-axis. Let's do another one with a whole. So here I can see that x minus 2 and x minus 2 cancel out. Now, I still need to set these things equal to 0. So if I'm setting the top equal 0, I get x is equal to 2. And if I set the bottom equal to 0, I get x is equal to negative 2 and x is equal to 2. Now notice, the x minus 2 is what canceled out, so that means I'm going to have a hole there at x equals 2. I am not going to have any x-intercepts because there's a hole where my x-intercept should be. So what we would say is we have a vertical asymptote at x is equal to a negative 2, and that's where this came from, and then I'm going to have a hole at x is equal to positive 2. Alright, the next one needs to be factored on top. Then set them equal to 0. There's no holes because I didn't have anything that canceled out. So I'm going to have my x-intercepts at negative 5, 0, and another one at 5, 0, so it's going to cross the x-axis twice. And I'm going to have my vertical asymptote is at x is equal to positive 4. Alright, some more rules. So if I have these two things on top of each other, if the degree of the top one is greater than the degree of the bottom, there is no horizontal asymptote. Now realize, up till now, we've only been dealing with the vertical, the up and down asymptotes. We haven't talked about the horizontal ones yet. Now if the degree on the bottom is less than the degree on top, we simply have a line at y equals 0. That's a horizontal asymptote. But if the degrees of the two are equal, then the horizontal asymptote is a line through y equals, and you just take the leading coefficient, so the number in front. So what in the world am I actually talking about? If I have this example, 6x squared plus 2x plus 1 over 3x squared minus 4x minus 6. Remember, the degree, and that's what we keep talking about, the degree is simply the largest exponent. Well, the largest exponent on the top is a 2, and the largest exponent on the bottom is a 2. They're both squared. So that means that I have the degree on the top is equal to the degree on the bottom. If the degree on top is equal to the degree on the bottom, I simply take the leading coefficient of both, so that's going to be 6 and 3. And I say y is equal. And that means that my horizontal asymptote for this problem right here is going to be y is equal to 6 over 3, or simply y is equal to 2, because 6 divided by 3 is 2. So recap, the degree is the exponent. Leading coefficient would be the number in front. If the exponents, largest exponents, are the same, I simply divide those leading coefficients to get my horizontal asymptote. Now let's run through a few more problems. Here we're going to have to answer all of the questions. We can now find the horizontal asymptote. We're going to find the vertical, the x-intercepts, your y-intercepts, and if there's any holes. The first thing we do is look for the horizontal asymptote, because I don't have to touch the problem in order to look for the horizontal asymptote. The degree on the top is 2. The degree on the bottom is that invisible 1. Well, if I go back up to what we just said, the degree on top is greater than the degree on the bottom, then there's no horizontal asymptote. So here, the degree on top is greater than the degree on the bottom, so I'm going to say no horizontal asymptote, or we could have said none. Next, our steps are to factor the top and bottom. The top can still be factored. Then set the top and the bottom equal to 0 and solve them. The bottom is our vertical asymptote. X is equal to 0. The top are our x-intercepts. So we're going to say our x-intercepts are at 4, 0 and negative 1, 0. In order to find the y-intercept, we substitute 0 into the problem. I'm going to do that up here, and I want us to think about it. I have 0 squared minus 3 times 0 minus 4 over 0. Can we ever have a 0 in the denominator? No, we can't. That automatically makes this no solution. But think about it a little farther. If our vertical asymptote is at x equals 0, that means that on the graph, our vertical asymptote is going right through our y-axis. If our vertical asymptote is going right through our y-axis, it makes sense that we can't have a y-intercept. And that is why We had a 0 on the bottom, meaning undefined, so our y-intercept is none. We don't have a y-intercept. Also, were there any holes? Can I cancel out any of the top and bottom? And the answer again is no, there are no holes. Now, if you were to graph this, because there is no horizontal asymptote, it's not a regular L shape. But also remember, we have x-intercepts that we need to cross. So I'm going to graph those at 4, 0, dot right there, and at -1, 0. So the graph looks something like this. Remember, you're going to come up and get really close to your asymptote, but not go through. And again, on the bottom side, you can come really close to your asymptote, but not cross over. And we're crossing the x-axis at our 2 x-intercepts. So the graph is going to look something similar to that. All right, here's another one. We have x squared minus 9 divided by x minus 3. Again, we need to check for horizontal asymptotes. My x squared is larger than the x on the bottom, which is an invisible 1. So that means our horizontal asymptote is none. Then we need to factor and set equal to 0. And that's going to give me x plus 3 times x minus 3 over x minus 3. Now I hope you notice that the x minus 3 and the x minus 3 are able to cancel out. What that means is that we're going to have a hole here. Now I still need to set these equal to 0. So on top I'm left with, and then on the bottom we do also set equal to 0. So since the x minus 3 is canceled out, the only x-intercepts that I'm going to have are going to be at x is equal to -3. Our vertical asymptotes, since everything on the bottom canceled out, I have no vertical asymptotes. The reason why I still solved for the denominator is to figure out where the hole is. There's no vertical asymptote because it crossed out, but I need to figure out where the hole is. Now the hole is going to be at x is equal to 3. Now there's going to be a y value attached to that, but as long as I follow the graph and wherever x equals 3 is, I put a hole there, then we're perfectly fine. We also need to figure out our y-intercept. We figure out the y-intercept by making everything inside there 0. Our y-intercept is y is equal to 3. Now let's go ahead and graph that. So when I graph it, it turns out to be a straight line, and that should make sense because we basically have y is equal to x plus 3, and that is what the graph is. The big difference is I have a hole. So notice that the hole is right here at x equals 3. So my overall graph is y equals x plus 3 because things canceled out, but there is a hole in the graph. And we said the hole is at the x equals 3. So where my graph crossed the 3, I put a circle there. And that's literally poking a hole into your graph as you put a circle where the hole is, showing that the line does not continue through that point. And the reason why the line doesn't continue through that point is because it would make your denominator equal to 0, and we cannot have my denominator equal to 0. All right, here's another one. First thing we want to do is factor this. Now notice how the x is negative, and I don't want that, so I'm going to factor out a -4. Now I hope that you can see that the x minus 3 on top and the x minus 3 on the bottom are going to be able to cancel. At this point we need to set them equal to 0. On the top we have x minus 3 is equal to 0, which gives you x is equal to 3. On the bottom, again, x minus 3 is equal to 0 because that's the one that canceled out. X is equal to 3. And then x minus 4 is equal to 0. And that means x is equal to 4. Now, because the -3 canceled out, this right there is going to be our hole. Our vertical asymptote is going to be at x is equal to 4 because remember the bottom gave us our vertical asymptote. Horizontal asymptote. Our horizontal asymptote is based off of the degrees. So we have a larger degree on the bottom versus the top. On top we only had an x, on the bottom we had an x squared. That means our horizontal asymptote is going to be the line y is equal to 0, and that just came right out of the vocabulary. Our x-intercept would be what's on top, and remember what's on top canceled out, so there are no x-intercepts. The y-intercept, we need to make all the x's become zeros and plug it in. So that gives me 12 divided by 12, which is simply 1. So that means our y-intercept is 1. Now, there's one more thing here. They want the domain. So remember, our domain is always going to be all real numbers except for either our wholes or our asymptotes. So our domain will be x such that x does not equal the whole or the asymptote. So x does not equal 3 or 4. Now, this question did ask one more thing. It asked us to determine whether the discontinuities are removable or non-removable. And this is basically what it means. If it is a whole, and we had a whole at x equals 3, we would say that is removable because basically we took a line and we punched a hole at x equals 3. So we call that removable. Then the vertical asymptote, that's not removable. That's a asymptote that we come really close to it, but we don't actually touch it. We didn't remove anything from the graph. So this would be non-removable. Remember, a whole, we removed something from the graph. An asymptote isn't removing anything, we just can't cross over. So we had the whole at x equals 3, which is a removable discontinuity. The vertical asymptote at x equals 4, which is non-removable. Horizontal asymptote at y equals 0. X-intercept, there was none. A y-intercept at 1. And the domain is all real numbers except x cannot equal 3 or 4.